Good evening, everyone. So I'm Engineer Shahid Mustali, Chairman of IT and Computer Engineering Section Committee. So thank you for being here with us today. I warmly welcome all of you all for the session on building a cloud native application jointly with Cloud Native Sri Lanka. I would like to invite Professor Ranjit Disanayake, President of Institute of Engineers Sri Lanka, to give a small introduction speech on our first public seminar on our session 23-24. Good evening, Engineer Mustali and the members of the IT and Telecommunication, right? Computer Engineering Section Committee. I think with this technical division, I work with the group heavily. I understand that they deliver a lot of important and interesting things for the not only for the engineers but also for the students of the various sectors. And as you know that this is the area where, for the time being, where we can bring a lot of money to the country. Therefore, improving this area is very much important as a nation, as we believe that the engineering is very much important for the regaining the economy that we lost. When we analyze the various different nations that they have come up from this battle, including Japan, Korea, Malaysia, Singapore, and so forth. I think they have, while they are maintaining the traditional business, right, they always try to capture the new market. For example, when it comes to the electronic area of businesses, Japanese who produced a lot of equipment required for the world. Likewise, the different time we see the different markets are coming into it. But I believe as a nation we have never identified that before, because without understanding the requirement of the world, if you understand once it is come, you will be late. So when you think about the world market for the tea, coconut, rubber, something like this, it is assumed like some amount of 100. The new market go like the thousands or 3,000 times of the market value in dollars. That simply say that but these markets are coming and going. So right now we are kind of getting closer to the IT market also, but they are, of course, we are not still too late. Therefore, training the engineers and the student for the market, still we have a opportunity to bring the money. End of the day, I think one of the main tasks we have as engineers in Sri Lanka, we must help the nation to regain the economy. Right? That is what I believe. Therefore, compared to any other sections of the engineering, we have electrical, mechanical, and various other areas, but this IT and computer is the one where we must make sure that to train the people. Therefore, I, as a President Institution of Engineers Sri Lanka, I would like to help whatever the way that you want to develop the section. Therefore, I have been asked for all sectional committees to come up with the year plan. Some of them already prepared, and as well as I asked them to go for kind of big seminar and the new activities. And when I look at the sectional committees, I believe that the sectional committee must develop up to the level of department. So department of civil engineering, like the department of mechanical engineering, like the department of the IT and computer. That's been because of the number of the students are increasing, because while we keep our activities in one frame, number of engineering faculties has developed, increased. Number of intake, whether you like it or not, increased by the government, and the technology faculties has come. We will have to take care of them too. And the private universities are increasing. So that means when you think about the 5-10 years before and compared to the, today, we have our role, or the workload coming to the ISL has increased 3-4 times. So if you are not going to take care of this workload, or the work that will come into us, number of requests, email, letters, and so forth, eventually we get the blame. It is obvious, right? Therefore, we as a ISL also must expand systematically, take care of the country's requirement, right? Therefore, we will get together and try to expand our activities possible ways, and make sure that the nation will be benefited by the engineering for the development of the activities. With that, I wishing you all the best, and as I have another program at the Cinnamon Grand, that is a Society of Structural Engineering AGM started like 5 o'clock. I'll be leaving very soon. All the best. Thank you so much.
Thank you very much, sir, for your guidance and excellent speech. So, without taking much of your time, let me introduce our speaker for today's session on cloud building cloud native application. So, Nilesh Jayananda, Principal Platform Architect at IT&CESC. It's very difficult to pronounce it, Australian company. So, Nilesh is a well-experienced software architect with 8+ years of experience in the information and technology industry. He has a proven track record of delivering exceptional results and strong expertise in cloud native application development, DevSecOps, site reliability engineering, product ownership, cloud computing, and software architect. Nilesh, over to you.
Thank you. Yeah, so the company I work for is called IT&CESC. I think when I first joined as well, it was very hard for me to pronounce, and then I got used to it. So before I start talking about this project, this particular topic, I'll just give a small explanation about myself and how I came here to be. So I think for the past 5+ years, I've been working as an architect in multiple companies, including WSO2. And those 5 years, I've excelled at building developer platforms, basically enabling developers to build platforms that enable developers to build these cloud native applications, right? So I have quite a lot of experience in this area, and I believe the insights that I'm going to share with you today is going to help you in your career and other stuff. All right, so let's start without any delay. And one more thing I'd say is, like, usually in Sri Lanka when you say 5:30, it's 6 that you start. But that's why there's a lot of people missing right now, but we'll come later. Right, so today I'll be talking about cloud native applications, and these are the areas that I will be covering. So microservices, obviously, containerization, DevOps practices, scalability and elasticity, resilience and fault tolerance, API first design, statelessness, monitoring and observability, security, and serverless computing. Quite a vast area, quite a lot to cover, and I don't think you can cover the whole landscape in a 1 hour talk. But I'll try my best, and I'll try to make it as simple as I can. And like, if you guys have like, let's not make this a lecture and you guys are just sitting and listening. But if you have any questions, any doubt at any point, just raise your hand up and we can have a discussion and go on from there. Yeah. Okay. So I think the first thing is, what is a cloud native application? I'm pretty sure a lot of you probably have worked with software, put them like hosted them, had URLs, and have accessed them and done all of that. So how does the software that you have built and the cloud native applications differ, right? The first thing is like, basically a cloud native application has a bunch of characteristics which I explained previously on the TLC. Basically it means that the applications built specifically for you to run in the cloud, utilizing the cloud, the advantages that cloud provides, right? So it can be any application, as long as it can scale, it has elasticity, it can use all the features that cloud is providing you, it is a cloud native application. But generally, cloud native applications do follow a microservices architecture, and they have this thing called logs, observability, security, and few other characteristics into them, which sort of like makes them cloud native. Right, so let's get on. What are microservices, right? So I thought I'd start simply, because I didn't know, probably there are university students and then there are probably experts here as well. So just to explain, back in the day when we developed applications, we would probably have a .NET app or a Java app, and then we would write everything in a singular code base. Every service, everything, and the way we modularized probably was we created Java packages or created folders and whatnot, and then we used those to build an application layer by layer, and then connect to the database and provide a full app, which can be deployed onto a VM probably back in the day. But today it's different. So there's this new concept, not new actually, it's old now, but it's called microservices architecture, which essentially means back in the day, when you broke Java apps into packages and blah blah blah, you now make them different apps. You create multiple small apps, which enables you to sort of like, and these apps are talking to each other via HTTP over the network and via ports and HTTP protocols. And each of these apps are now segregated independently, and they have their own databases. And that's what microservices architecture is in a nutshell. Right? That's how when you design new applications, you sort of like, you don't build everything and put all the code into a single app, single server, but rather you break it off into smaller components, smaller services, and then you get them to talk to each other and then work together, thus making it a microservices architecture. Okay, moving on. So these are sort of like the features of microservices. Like for example, if it's a monolithic application, as you can see from the diagram, when you are scaling and stuff, if it's a big monolith, probably requires more resources, and scaling means you have to scale the entire monolith multiple times. But if it's a microservice, that's not the case, where you can scale individual services independently. Like for example, there was Black Friday days recently, and let's say marketplace application or Daras, let's say, was built with, I don't know what their tech stack is, and assuming if they have built it as a monolith, what would happen is for Black Friday days, there's a lot of people buying stuff and doing a lot of things. They would have to scale the entire monolith. And let's say the monolith to run Daras as an application would take about 4 GB of RAM and 2 CPU. you have to scale it up. If it supports horizontal scaling, you have to scale it up multiple times, and that's giving you a lot of resource cost. If it was a microservice, and if Daras was broken it into like login as a service, and then product catalog as a service, payment as a service, etc., different services, only product catalog and payment will have to get scaled, and the others can remain the same, right? In that way, your resources are better optimized, and you won't be spending as much as it would be as of a monolith, scaling a monolith. So that's basically what scaling is. And then, how small should a microservice be? Jeff Bezos said, if you can't feed a team with 2 pizzas, it's too large. But my team, there's quite a bit of people who can eat pizza. So yeah, but normally the rule of thumb is you can have around 12 people a team, and that's pretty much it. So more than that is just too much overhead, and you probably won't get a lot of things done, right? And the size of the microservice actually depends on your requirement. Ideally, what I would do normally when I design products, I break it down by domain. It's easier. So break it down by domain, like let's just log in, like authorization is one microservice. It's just something else that you're going to do. Like you can actually like imagine you are building a monolith back in the day, and how you would package your Java application, like make it into folders, right? Those folders can now be services. That's the exact same way you would sort of like draw the boundary of microservices. Otherwise, it's just you can even break by function, but that's just too much. So it's just domain is the way to sort of like make a microservice small. Right. Then the next one is organized around business capabilities. This is again a feature of microservices. Back in the day, the companies had DBA specialists, middleware specialists, UI specialists, and all of that. Today, that's not the case. We have cross-functional teams. Everybody, like each team has a subset of all of these, and then they work independently on their product or service, and they are responsible for it. And that's how you can scale and grow. Otherwise, in the traditional manner, what happened was the typical thing that we all used to know, like the ball pass, right? It's not my fault, it's DBA's fault, or it's talk to the UIs and stuff like that. But yeah, so with this, we have with cross-functional teams, the responsibility is given to a specific set of people, and then they are responsible of managing the application end to end. That's what we mean by organized around business capabilities. Then I think we already spoke about this componentization via services. So I'm going to skip this. Right. The other one is decentralized data management. Here, what happens is for each microservice, when you normally design microservices, you wouldn't point all the microservices into a single database, but rather you create multiple databases and make these microservices independent as possible. But in technical terms, what this means is doesn't like if you take AWS or Google, you don't go and create multiple AWS database instances, right? You create one instance to your project, but you have multiple DBs in that. That's how you do it. And then if let's say one microservice requires a lot of resources and all, you can actually take it out and put it into a different database instance. But typically, what we say is we use 1 DB per microservice, and it's not recommended for you to sort of like write 2 microservices that connect to the same database, because then there's no ownership of data. If one microservice changes and does something wrong, and the other microservice is obviously going to fail, and there's going to be issues, and then you are going to get into a hole where debugging what went wrong and who did what. You keep everything as separate as possible. And finally, support for technology heterogeneity. I pronounced that right. But what this basically means is, today if you are building an IT team, right? And if you're hiring a bunch of people, a lot of people have different experiences and skill sets and expertise, right? And if I hire a bunch of engineers who are fresh grads, now modern day fresh grads are mostly, I think, excelled in Node.js, right? And also Python, probably the ones who have done AI for university projects. So yeah, they are, and then PHP, not a lot of resources right now who know. Java and .NET, there are a few, but not much. And if I hire a bunch of Node.js engineers and I tell them, hey, write this in Java or .NET, they're going to struggle, and the team efficiency and the team performance is going to go down, because then they have to learn, they have to do R&D. The way you write in Node.js is different the way you write in Java. So one key factor is when you're architecting and making these decisions, take into account of what your team is capable of and what their strong points are. And the second one is actually look at the requirement as well. Like or let's say you have a bunch of Node.js engineers and you have this AI project or ML learning project, right? Then obviously you have to use something like Python or something. You can't ask them to write in Node.js. So you have to make that decision, and you have to make a proper decision on that. But what enables you to do in microservices story is, like when I said, like you can break it into multiple services, right? So you can actually have one service in Node.js, another one in Ruby. I mean, I don't think Sri Lanka there's a lot of Ruby people, but yeah, you can write one in Python, you can write one in Go. So there's a lot of options, and you are not constrained anymore. So that's the advantage of going in that path. And also, you don't have to be constrained to the database as well. You can have a relational one, you can have a DB, you can have whatever you want, depending on your requirement and the project needs. Right, the next one is called design for failure. In theory, microservices, we tell that a microservice failing independently should not affect the entire system. But technically, it does. Because at the end of the day, when you do send a request or when you want to do something from your application, it's a bunch of microservices talking to each other, making a chain reaction, which gives you the output. So realistically, multiple services will be talking to each other, and hence there will be multiple failures instead of one. But when you are designing microservices, you have to expect this. So because microservices are always communicate over the network, and we have to always assume that network is not stable, which means there are ways you can avoid this. So you have to plan for failures when you are designing microservices. So it fails more than running and doing your own, writing a monolith. Because if it's a monolith, it's just you have the variables, you have the typed variables, if there's a difference, and the error would show up at the build time and all of it. But if it's a bunch of microservices, you only have the API spec. But if the other team who builds microservice A or whatever changes the API spec, and you are the owner of microservice B and you don't know the change, then it's going to break. So there are stuff like that. So you always have to design for failure, and expect failure to happen. Right. So this is where it comes to resilience and fault tolerance. So few bullet points here. So the first one is designing it to be stateless. Back in the day, I remember in my university, I think second year, there was this lecture, a whole lecture dedicated to sessions in PHP, right? But today, I think building cloud native applications, we don't use sessions, because in-memory stuff that we use, what happens is it gives application a state. And when you design cloud native applications, these has to, we have to treat them as if like they can always, die and they can come back again and all of that. And if it had state, then it would have problems, right? The data would be lost. So it's always recommended to take the state out and put it elsewhere rather than keep it within the application. One simple example would be a photo upload app via PHP or something, where a user would click a button and upload a picture, and the file is actually saved within the application inside a folder called uploads. So now because this is within an application, the moment application dies and comes back again, if it's a container, that upload will be gone. Or if you had a shopping cart, and then your user, you have added so many things, your probably wife or somebody shows a lot of things, spent hours, and then something happens to the application restarts, it's gone because the state is in memory. The shopping cart is in memory as a session and it's gone. So it's better to take this out and put it in a Redis or MySQL or something, so that when the application also restarts, it can actually get it back and then do what it's supposed to do. The next one is called load balancing and circuit breaking. I think everybody knows what load balancing is. You scale an application horizontally, you have multiple instances, you put a load balancer in front, and the load balancer is now capable of sending traffic to the available instances. But probably don't know is circuit breaking, which is basically, let's say that there are a few ways to handle this. The first one is timeouts. Like let's say you send a request to an instance and you wait for it to respond, and if it doesn't, you resend it back again, and the load balancer would send it to a different one, and you come back. So that's what technically circuit breaking is, but with a little bit of advanced logic. For example, you would try, and depending on the responses that you get, 500s, 401s, etc. from a service, your load balancer can intelligently determine that a certain instance is not doing well enough, so that it can actually stop sending traffic to that instance, rather send it to other active instances who are giving a better rate of 200 responses. That way, you give some time for that one that is behaving in an odd way to recover and then get back to its normal operation state. So that's what we call normally by doing circuit breaking in like network traffic. So then the other one is fail fast and fail independently. Like failing fast, of course, when you try when you send a request or something, you probably can do a small timeout, and then fail independently, and then faster startup time. Like if your application dies, you don't want your application to take about 10-20 minutes to spin up again and be ready to sort of like accept traffic, right? Application has to be within 60 seconds, it has to probably be up and running and be ready to accept traffic. So those are the things you have to do, and I personally know certain legacy applications take about good 5 to 10 minutes to start up and be ready to be able to accept traffic. So those things in the cloud native world is not good enough. So probably writing from languages like Go, Node.js, etc. gives you fast startup times, and even Java, etc. I think the problem personally I've faced with Java is to bootstrap a Spring Boot app, it takes quite a bit of CPU, but after that it doesn't. So if you do limit CPU, it takes some time to bootstrap, but if you give a lot of CPU, it quickly bootstraps, but that CPU is now lost. It's completely dedicated to that application and no other application can use it. So there are issues like that. There are ways to handle it as well. High availability again, availability zones, and make sure your application is always available. And also, like if you're coming from a Kubernetes background, etc., when you're doing clustering, just because you have 2 instances of your application doesn't mean it's highly available. You have to make sure your application is in 2 sort of like virtual or physical, like in Kubernetes, 2 nodes, or if it's a VM, it's 2 VMs and in 2 separate zones or whatever. If you have two containers or 2 application instances running on the same VM, if something happens to the VM, you are not highly available. So that's something to keep in mind. And finally, health checks. So there are 2 concepts for health checks: liveness check and readiness checks. So people who are building cloud native applications should write these. Some people just do a simple return of 200 for HTTP GET or whatever for liveness and readiness. But ideally, what you should be doing is probably check your database connections and see whether everything that is your application to be performing is available, and make that check and give a return saying 200 or say I'm not available. So liveness is basically, if liveness fails, usually the queue is to delete the application, like kill the service and restart it. If readiness fails, the queue is normally to stop sending traffic for a while. Let me let the application figure itself out and then send later. That's the concept between liveness and readiness in the cloud native world. Right. So I've been talking a lot. Any questions up to now? Or am I boring you? Right. The next one is rate limiters and load shaders. I think everybody knows what rate limiting is. Basically, you get hit a bunch of times and you have a rate like 1,000 requests per second or something, and after that you stop accepting traffic and you let it go. But there's another concept called load shedding, which basically means you don't, in rate limiting you stop everything, right? But in load shedding, what you do is basically you pinpoint and keep a bunch of APIs that you deem as priority APIs, and then you have ones as low priority APIs. So you stop the low priority ones and you only pass through the high priority one. One example is premium user versus paid user. And during Black Friday or whatever, if there's a lot of load and if you don't have enough infrastructure to handle it, you will probably have to make that decision saying, all right, these set of requests shouldn't come through. Only these set of requests should have more priority, something like that. Right. Then comes API first. So when you are developing a cloud native application, API first is the way to go. Like even when we are designing, what we usually do is in a common, starting from scratch or building a feature, what we would do is we would first write down the API spec that is needed for that application, which is good because you can actually mock that, because these are microservices. The service that you are building will be used by other consumers, like it could be another service, it can be a front end, whatever, right? So by writing the API spec, and then you can actually quite easily mock it as well. So before you actually do implement the service, you can write the API spec and mock it so that others can actually start integrating it without waiting for you to sort of like finish implementing your service. So that's, and the other thing is in the microservices world, we tell them that the services always interact with each other over the network on HTTP interface. It can be HTTP, WebSockets, or gRPC, or even eventing, but it's always over a network, and it's recommended to be talking over interfaces of HTTP APIs, right? And the other one is use of API gateways, which I'll come to next. Okay. So as you can see from the image to your right, to your left, I presume, is a monolith app which has everything. Not even a monolith, we can call it as a microservices as well. So it has authentication, it has APIs, rate limiting, retries, caching, everything embedded into the service. So let's say in a heterogeneous world where you have one API in Java, one API in Node.js, another in Golang, you have to now use different libraries to enable a common auth, common rate limiting, retries, caching, etc., which is not ideal. It's sort of like grunt work, to be honest. But if you do implement a proper API gateway, you can actually offload these into the API gateway. So now the API gateway can handle authentication, it can handle managing your trace IDs, it can handle the retries, it can handle caching, it can handle everything. This way, your team, the service people who are writing the service, can focus only on the business logic and let everything else be offloaded into the gateway, which is quite easy. Okay? That's another thing about cloud native applications. Yeah, sure.
From the other side is showing authentication separately. But to say to access a microservice in caching, you first have to get the authentication done. No?
Yeah, so sorry. So this is the
Yeah, left side one is clear because first you
yeah,
have to authenticate.
all right, okay.
But the right hand side,
Okay.
you have to be authenticated. No?
But that handles to the API gateway, isn't it?
Yeah. So first you call the API authentication, and then you call the API cache.
Right. So how we do it and how everybody else probably does it. So when you talk about authentication, one thing is there are now it's quite unnatural. Like in the cloud world, we have Cognito and few other. WSO2 also has something called as Gradio. So they have their managed services for authentication, right? So what essentially means is the API gateway is gonna get the request, hold it, talk to that external service that does manage the authentication authorization, comes back. If it's true, forward it into the actual microservice. Yeah, and if you're not using external authentication services, you can have another microservice for authentication and implement the same logic, which would talk and then come back and then you forward. Yeah. Okay. All right. Right, then tracing. So although I talked about tracing here as tracing on the API gateway, there's no magic solution for tracing, right? It always includes you have to write some code to implement proper tracing. What API gateway or service mesh or whatever that tells you that they are going to give you automatic tracing is basically they are going to intercept your request and inject a trace ID. But properly utilizing it is completely up to you, and that is at the code level. For example, let's say there's service A, service B, and service C, and A talks to B, B talks to C. Now you are sending this request through an API gateway. So API gateway injects a trace ID which goes into service A, which is fine. Then service A is now calling service B. Let's say it's again going through the API gateway for example. Now, if the API gateway, if you probably have in the service A, you have to get that trace ID that is incoming from the API gateway and then reroute it back to the next call that you are making from B to C. Otherwise, what happens is it's going to be a new trace ID. And then you can't actually track that from like the traffic that came from A to B is traced from B to C. It's going to be looking like two different requests rather than one single chain of HTTP requests. So that's why you need to add some code, because there's no magic way to sort of like figure out like from one service going to another whether the context of that HTTP request has an incoming one or not. You probably have to insert the trace ID yourselves when you're sending additional requests, chaining requests. And to visualize, of course, there are Jaeger, Zipkin, and cloud level stuff. You can easily get good outputs. Right. So that's it about microservices. So there's this concept called 12 factors. This was brought on by Heroku back in the day when the whole monoliths and microservices were a new thing. And when Heroku was out, they had this concept called function as a service, where you can simply put a Node.js code on Heroku and you get a URL and you can execute, right? But the problem was people were still, thinking in the manner of monoliths. They were managing states and doing all of those things. So they came up this set of factors that enable developers to think in a more cloud native way and write more function based applications. So the first one is one code base, one application, which essentially means one like there's a concept called mono repository and multi repository, right? Basically, if you are building a big app, you have the choice of either creating multiple repos or a single repo and then put all the apps in. But the recommendation is, one code base, one application. Essentially, and there are scenarios if your application is sort of like tightly coupled with another service, it's okay to put it in the same repository because you probably have to share the interfaces and all of that between rather than having to rewrite it again. But if it is loosely coupled, I would recommend you to have maintain multiple repositories, because the next steps like CI/CD and everything, the eventing that we do, they are all based on triggers, and every time there's a merge or something that's happening in the code base, if everything was in a single code base, there's going to be a lot of services getting built and a lot of them getting deployed at the same time. API first, we already spoke about. The next one is dependency management. I remember back in uni days, we had this thing called internet project. I can't remember, but the idea of it was we had to get 8 people together, and each person has to do a CRUD operation, and we had to build this one huge app. I remember we did it in Java, and a bunch of us downloaded Java files and added functionality, and we didn't know Git back then. So it was all about copying through thumb drives to another laptop and then merging together and hoping that it would work. So those are the days. So I remember one time one of my colleagues just pressed replace all and merge, right? Which essentially meant like certain libraries were gone, certain code was missing, and everything was gone. And luckily I got an A, but yeah. So if it was dependency management, if you use like in Java, it's Maven, in Node.js, it's NPM, Go has its own thing. So using those makes sure that your dependencies are in order and the sub dependencies and the dependency tree is always up to date and is always working fine. So that's one of the key things to running stable software. I think even monoliths now have dependency management. I rarely see people downloading Java files and manually adding those libraries. Next one is design, build, release, run. Basically CI/CD. I'll get to that in a later slide. I think the fourth or the fifth one is configuration, credentials, and code. So here what happens is make your application as generic as possible. And if you really look at it, when you do deploy applications in enterprises or anywhere, you normally have environments, right? You have a development environment, you have a production environment. The idea is you don't build again for all of these environments, rather you build for one environment, and the only things that change is the configuration, isn't it? The database URLs, the passwords, and all of that. So inject, get them as environment variables rather than hard coding it or committing it or whatever, right? So that's the idea of this particular point, configurations and credentials. The next one is logs. Again, in monoliths and etc., what happens is all the logs are written to files, isn't it? And then we have this whole huge log management problem as well. So in 12 factors, what they tell you to do is treat logs as streams, which essentially means if you want to log something, you put it to the standard out of your process, and then let the underlying platform that's running your application to handle the logs, rather than give your let your application handle the logs by themselves, right? So you have to put either standard out or standard error, and then let the underlying platform to manage the logs. Disposability is basically application being able to quickly get killed and respawn up again without having to have a loss in service. Backing services. What backing services means is if there's a database or whatever that is, depending on like your application is dependent on it, treat it as the whole thing as a single app, and then those has to be well defined APIs, and treat it as one component. So a database and the code base sort of like becomes a single application in a microservice. So that's basically backing services. And environment parity, what it means is keep your environment like development, staging, production, etc. as close, like similar as possible. Not much changes, because the moment there are changes from development to staging or staging to production, there's going to be errors, right? So keep them, the infrastructure and everything, as same as possible to have a better experience and to avoid a lot of errors. Administrative processes. So what this basically means is, anybody know database migrating? Yeah. So our migration basically means is, we have the whole ORM concept now, right? We don't write SQL queries anymore to create table and do all of that. What we do is we define some classes, and then we connect it to the database, and they automatically create the tables and do all of that. So we call that migrating, by the way. And rather than automating this, run it as a singular administrative process when the application is updated, to update the database with the new migrations. Because the problem is, if there's a breaking change, and let's say that for some reason your application is doing let's say in the modern world, we don't do we do rolling updates or like blue, green or whatever. So when we do that, if there's a breaking change, the older service will, the running service will have issues. So it's recommended to somebody who has administrative privileges to run this properly, and rather than let the application automatically do it, to avoid sort of like errors. Then port binding is similar, like exposing application over a port and being able to access it over HTTP, and we can change the port and map it to different ports and do all of that. And finally, the 12th factor, stateless processes, which we discussed. So your application should run as one or more stateless processes, which essentially means even if they get killed and they come back up, you won't lose any service or data. So those are the original 12 factors given by the Heroku guys. Then with the cloud native world, there are 3 more added. One being concurrency, another being telemetry, and the third being authentication and authorization. I think authentication and authorization we spoke about. That's the concept I was going to talk about here. So concurrency is your application being able to scale and run multiple instances and not being able to not have any errors. Now one example is, let's say you have an app, and this application you want to do a periodic check of something, right? You want to run some migrations, or you have to sort of like extract some stats out of a database and put it into a different table, right? And you want to do this hourly, and you have written this with a timeout on your code. So your main server is running, and there's a logic happening, which is like every 1 hour or something, there's a certain code getting executed. That's fine, it works. The moment this scales horizontally, what happens is, now there's 2 instances running, right? Which essentially means now 2 of them every hour is now extracting stats from the database. And the more it scales, the more times it's going to extract the stats. It's not going to be hourly anymore. It's going to be, I don't know, depending on the number of instances that are running. But rather than that, what you can do is make it a different process. Take it out, write another service or whatever that would do a HTTP call or something that would trigger stat migration, so that if there are 100 instances running or whatever, the load balancer would only hit 1 and it would run the stat hourly, and then that's it. Telemetry, again we spoke about. This is all about observability data, the metrics, CPU, memory utilization, tracing, and all of that. We'll have another slide for that. So that's it about 12 factors. Any questions? One.
So other load, other load, load like smartphone handling roles in our own system, we really the standard out and ready to handle by an online application. So only macro things like are we putting listener on the standard out? To solve them by online system or
Yeah. I can. So before I answer, I just want to know your background. Like, are you referring to running it on our data centers, or are you referring to cloud here? Okay. Right. Okay. Fair enough. So if it's cloud, also cloud, obviously the definition of cloud native application is utilizing the features of cloud, right? So by making, like, if you do run your service as an AWS Lambda, hypothetically, and let's say that you are writing logs into a file, I think it's going to be hard for you to read those files, those logs. But rather, it's easier for you if you put it into standard out. You can read it quite easily from CloudWatch. I believe that's a service. Similarly, in a VM, if you do the same thing, you would just write a standard out, and these standard outs are going to go to syslog and etc. on the VM, which can be used to their other services like FluentD and FluentBit, which would do the log streaming to an external service like CloudWatch, Datadog, whatever, right? But if you are handling your logs yourselves, the problem is, then let's say there are 5 applications and these 5 services are handling logs by themselves. So now you have the issue of managing these logs independently and then shipping them into some log aggregator so that you can view them, right? But putting it into standard out and making it a stream makes it easier for everyone to sort of like read from a single place, aggregate the logs, and trace it properly with all the other microservices and get it done. Yeah, does that answer your question?
So can you elaborate more on the mechanism that you use to like the failures in microservices? Are we like building after this services or like how we found those failures to like keep the content properly?
Right. So the first thing is your microservice needs to be designed to handle failure, right? If your service is talking to service B, you have to always assume that it's going to fail at some point, and your service should be able to handle it without breaking functionality or like crashing the system. I think stopping the crash is the main thing. So try catch and all of that. The other one is how do you monitor it, right? So basically monitor it by the 200 response codes that you get, right? So if you have a lot of 500s or 400s, you can deem that particular microservice is having some issues, and you can go dig deep and see what's going on, right? But if it's if it's a random 500 here no there, then you can just avoid it. So it completely depends on your your requirements of the project and how it is going on, right? For example, let's say that there's a huge application written which goes to the emergency services, right? You press a button and ambulance comes to you. So if there's a 500 on that, the life will be lost, which is critical, is bad, right? So that you have to sort of like, even if 500, you should get alerted and you should sort of like check it out. But if it's a normal application which is non-critical, couple of 500s, 3 or 4 is fine. And then there are other log-based alerts that you can do. sort of like tracks regex expressions for error or standard error, and then gives you alerts, which your support team can look into and see what's going on. So those are the things you do. Yeah.
So, you training for your like technical way. So like it is not a like very sensitive or like future event. Like you don't need to raise circuit break and like I think backup services to sound.
So I don't understand the term backup services, but let's talk about circuit breaking, right? That is all about resilience. So here now, there are two ways a service can fail. One being actual code issue, right? If it's an actual code logic issue, obviously you have to do a fix and patch it up. It's no magic, no circuit breaking can fix that. The other one be the resources or the garbage collection and all of that playing a part in a crash, right? So in such a cases, by doing circuit breaking, essentially gives your service like, now your service is not independently running, right? It has multiple instances. So when these things happen, usually one or two instances are affected, the others are running. So what circuit breaking does is fail fast and then come back and then send it to another instance that is working, which would give you a correct response. That's what circuit breaking does. And the ones that are returning a lot of 500s or 400, the load balancer can actually exclude them for about 5 or 10 minutes and give them some time to cool off and then send request back again. That's it. Yeah. All right. Right. So, all right. So this is basically why does software break in production? This is a common thing. I think I've probably experienced this in my life. You put a push to development or staging, or like have a colleague over here, and I recently what I did was I put it and then I said this is working, and he was like it's not working on my machine, and I was like but it worked on my machine. But yeah, that's the whole portability thing that comes into play. So by containerization, I think about 90% we achieve portability. If it works on my machine, it would definitely work on your machine. There are exceptions though, like .NET apps and etc., which has DLLs, and your Linux doesn't have those DLLs to run it. But other than that, it's like normally containers are pretty portable. And it also has isolation properties. So containers are bundled with application code and the supporting libraries that are needed in them. For example, you can't really run Java, I don't know what newer Java versions are, but hypothetically, let's say Java 8 and Java 10. You can't run it in the same machine. I don't think you can. But with containers you can, because those are two isolated processes and the Java binaries are running attached with one container process, and the other Java 10 libraries are attached with another. So you can quite easily do a lot of things and virtualization under that. I think, yeah, probably you guys know a lot about containerization, so I'm not going to go much deep here, but if you have any questions, you can ask. Okay, no. Right, so I think containers versus VMs, this is what I meant here. So back in the day, when we created VMs, infrastructure was there, we had the hypervisor, and on top of that, we would dedicate resources per virtual machine in which we would have the guest operating system and the application running on it. But in the containerized applications, that's not the case, where we have infrastructure, host operating system, and now Docker or the container engine plays the part of the hypervisor, and using a single host operating system, we can run multiple applications, thus saving resources. However, if you go to AWS, Google, or Azure, there's still the option to create VMs. The problem is the containerized applications make sense for a single tenant, but not for multi-tenancy. As a security aspect there, because see, application A, let's say it belongs to me, and application B, let's say it belongs to you. If it runs under Docker, under host operating system, there's a high chance that if I'm a good enough hacker, I can actually exploit some vulnerabilities in the root system and then attack your application or gain more information or do something, right? But still, there are ways you can stop that. I think AWS Lambda runs as containers, but it uses something called Firecracker underneath, which does the isolation. Google App Engine does the same thing, has something called, can't remember, something space gvisor, something called space kernel. So it's another area. Happy to talk about it after this talk if you want to know more. Right. So containers and microservices. So back like the idea is you put an application or a service in a single VM, but now we can actually bundle an application as a container, as a Docker image, and then run as a container and then scale it massively from there onwards. Right. So then comes the problem, orchestrating the containers. And let's say you have like normal microservice based architecture, you have minimum 10, 15 services, right? Let's say each service scales to 5 instances. If it's 10 services, then you have 50 containers to worry about. So it's not easy managing 50 containers yourself, manual, doing Docker up and all of that. That's where orchestrators come in. So what orchestrators basically does is we tell, hey orchestrator, I have this Java app, I want 3 instances of it, and here are the VMs that these should run on, and the orchestrator would make scheduling decisions and resource allocation and do all of that and make sure your containers are running and to also do the load balancing, right? That's what orchestrators do. And the most popular orchestrator is Kubernetes. There are others as well, but the most popular one is Kubernetes. And orchestrator can quite easily, we can dedicate a bunch of nodes or VMs and then ask it to do scheduling, scaling, allocation, and do a lot of things that we otherwise would take days to do manually, automatically. That's what orchestrators do. Any questions?
So databases, so they generally recommend to keep the database outside of the content with the consistency of the database. But then again, the container is also growing like the PushDB, Cassandra. So once you are there, have to keep all the most critical.
Hey, you had to go with the advice of the vendor for that. If Oracle says run it on VMs, you can't run it on Kubernetes because then Oracle won't support it if something goes wrong. But I think there are 2 aspects, right? Again, Oracle database, like they've written it to support to running on VMs and having dedicated bunch of resources, and they probably don't support containers getting killed and restart and all of it. Those are like, keep running, the server keeps running and that's it. You don't touch the server sort of a thing, right? Oracle. But I think Vitess and few other container-based databases, they support scaling massively, like quickly spinning up more instances and then scaling down and then optimizing your queries and do all of that, and then talking to underlying storage as well using Ceph or whatever APIs. And so they've written it in such a way that it works, right? But so you had problems with the vendor for that. 2 ideas. So I would personally recommend MySQL and stuff not running on Kubernetes, because there's no point in running it in Kubernetes, right? Because it's a stateful database. MySQL doesn't scale it. You only scale it vertically, right? You don't scale it horizontally. So there's no point of running it in Kubernetes. But if there's a like cockroach, I think scales horizontally. Makes sense to run on Kubernetes, right? That's where the logic is. All right. Right. All right. Another key aspect of microservices and cloud native applications is DevOps practices. And according to a study done by Google, actually 70% of the outages are caused by changes in a live system, which is true. Uh, if there's something working and if you don't touch it, it would work forever. But you keep adding features and doing a lot of things break, human error occurs, and you get called in the midnight over a weekend, and the weekend is gone. That's what happens. So, how do we avoid this? How do we do change management and ensure, at least for about 90% or 95%, that the applications don't crash and you can have a good weekend? So these are the sort of like concepts that allows you to do it, but of course implementing these is a different matter. Of course, each application would have continuous integration. Gone are the days we would copy files into a server using FileZilla or something like that. I worked previously on a bank early in my career, and we had this check printing system. Every time we did the update, there was no Git or anything. We would just use FileZilla and then FTP the files and replace the stuff that were in the server. If there was any error or something like that, that day checks won't get printed. So tell the bank, but I think now they're doing it in better way. 10 years ago. So yeah, so unit testing is one thing in a continuous integration. So unit testing, it's part of developer discipline as well. So they have to probably run. A common practice today is if tests are failing, you commit the tests and you commit. It should pass and then it would go to production, and then only you would have problems. I think, yeah, you are smiling because you did it today, right? So yeah, so he's in my team and he did it today, and I told him not to do that. And then the other one is quality testing. So using something like SonarQube, there's CodeQL and few other tools available. We should do quality testing, and they would actually do a logic test as well, and actually tell you like if there are any errors in your logic, you should use a while loop instead of for or whatever. They would give you those suggestions and make sure the quality is there in your code. Something that I couldn't put here is another developer discipline, which is pull requests and peer reviews. So all of these can be automated. I know ChatGPT is also quite good these days, but still nothing beats review by another peer developer. So PR should be reviewed by somebody, and then yeah, but I think even I'm doing this, it's like if there are about 30 or 60 files, nobody reads them, I just approve and then say all right, good to go. But technically you should test it, try it out. The other one is vulnerability testing. These can be automated, so you can make sure that you don't accidentally commit any sensitive information into your code, and also make scan your dependency graph and see whether there are any known vulnerabilities available which could potentially be used to attack your system. So those can be done. The other one is integration or the API testing. The thing about having multiple microservices is if one API spec changes in a singular service, the other services will get affected and you will get a degraded performance, right? So the only way to stop it is to do proper API testing, integration testing, basically, to make sure that your new service is working with the existing system. So it's really essential in a microservices world to do integration testing before you do the deploy. Load testing depends on the use case of your application, and if you're expecting a high load, it's better to sort of like mimic that load and see whether your application is capable. Otherwise you will be in for a surprise. And then artifact registry. So here what we mean is like the builds that you do, you push it to a registry, if it's containers or npm or whatever, so that you can do rollbacks quite easily. If there's a previous build, you can do that. That's continuous integration. Next comes continuous deployment, which is again quite important. Not just building the application is one thing, properly deploying it into the environments that you have in your company without having a service downtime is another thing. The critical thing is promotions from one environment to another. How do we seamlessly promote? There are multiple ways to do this, and there are release strategies as well. So when I earlier talked about 12 factors, I spoke about environment parity, and the whole concept is you build once to a single environment and then you promote that build across the environments rather than build again for new environments, right? And the more the environments are similar, less errors you are going to get. And then we have release strategies, blue, green, canary, rolling, etc. I think rolling is the most popular one because it comes out of the box in Kubernetes. But to do blue, green, or canary, you need bunch of configurations and additional tools on top of Kubernetes or other stuff to do that. And then there's something called release metrics, DORA metrics, if you have heard of it. So this is what defines the engineering capability of a company. So basically deployment rate means number of deployments you do to the production system. Lead time to change means how long a commit takes to get propagated into production. Change failure rate is the rate of failure per changes that you make in production. Mean time to recovery is when you have an issue, production level issue, how long it takes your team to resolve it. Basically resolve the support ticket, right? With these metrics only, they determine the level of your company's engineering capability. Usually, the ones that deploy every day, multiple deployments a day, usually less than 24 hours of lead time to change, etc., are deemed to be at the highest level of engineering, and they are the people like Google, Netflix, Apple, etc., right? And then the next stage, and likewise it goes. That is continuous deployment. So I'll just walk you through the deployment methods. I think my time is also 10 more minutes remaining. So Highlander, not the cartoon. So basically what this does is, if you have V1 running, you kill V1 and you immediately switch to V2. That's Highlander. Canary deployment is basically, if you have 3 instances of V1 running, you kill one off and you put V2, and now in this case 33.33% of traffic is going to V2 and 66.66% traffic going to V1. And then you can leave it for a while and see whether your V2 is doing well, and if it is doing well, you can just do the update the rest of the instances as well. Rolling update is quite simple. Basically, you kill one off, you update with V2, then you wait till it gets ready, and then the next one gets rolled down. The problem with rolling update and canary deployment is, let's say the moment in the second picture V2 is active and ready to accept traffic, it would start rolling down. Like, let's say you have an endpoint called get users, and get users, there's a critical bug, right? You probably forgot to add a try catch or something, right? In a rolling update, V1 will get replaced by V2, and then you will probably have to do a rollback. But in Canary, what happens is, now you have the power or the control to make the decision when to update all 3. So when V2 is updated on load balance at the second picture, you can actually wait for a while and see whether all the traffic is working and whether it's behaving as expected. So when the get users is hit, it would fail and you would know there's an error. So you can roll back only this one, and only 33% of the traffic will get affected. In this, it will probably mean a downtime. There would 100% of the traffic will get affected because the entire thing is rolling updated, and you have to sort of like roll out or roll down the release. Blue green is a bit expensive. Basically what happens is you have v1 running and you have v2 running, and you would, while v1 is running, you would send traffic to switch traffic to v2, and if everything is okay, you would decommission v1. If there's problems, you would go back to you would again change the traffic to v1. Sort of like you have a hot water bucket, and then you put your hand in and check whether it's hot or not, something like that. That's what blue green is. Right, any questions? I'm into the last couple of slides. So configuration management is the other thing. So there's this concept called GitOps in cloud net. This is all about managing the infrastructure that your application is running on. So you have two options, right? One thing is you log into AWS or VMware, whatever, click, create the instances and create the services and get over with it. But the problem is that it's not replaceable. Like for example, the person who does the click leaves the company, and the next person who comes in doesn't know what resources has been created and all of it. And when you're actually migrating from one place to another or replicating that environment, there's going to be quite a bunch of problems. So because of this, there's this concept called GitOps and infrastructure as code. So basically, everything that you do, the infrastructure, whatever, is written as code and then put it into Git, which is great because it has the whole versioning and revisioning and all of that. So you can quite easily maintain, roll back your changes and do all of it and ensure that your applications are running properly. Finally, observability and monitoring. I already spoke about logs being events. So the other ones are resource metrics like CPU, memory, network, traces, and also alerts. I've seen a lot of companies have this quite nice dashboards. And then when I'm designing products also, because I told you I'm designing dev products, right? Which means, so what they want to see is dashboards, right? But actually, more than dashboards, what you need is alerts, because having fancy dashboards doesn't mean anything. Alerts are the ones that are critical, which would give you an indication of what's going on, or whether something is going wrong, or whether something is about to happen. Dashboards are a way of you debugging something or getting to a root of something to figure out why this is happening. So alerts take priority, then dashboards. And dashboards can be, depending on your use cases and the issues that you get, you can have customized dashboards for you. Finally, finally also, but this is actually the last slide. Serverless computing or function as a service. So here what happens is AWS etc. have this AWS Lambda, Google have Google Cloud Run, Cloud Functions, Microsoft also has something. So what happens here is developer can 100% focus on the code and then deploy onto these services, and they manage scaling and everything that I spoke up to now. They manage it by themselves, the cloud vendor, and we don't have to worry about it. But the problem here is there's no control over the things that you need. If it's a basic scenario, it's fine. But if you need more control, then function as a service probably isn't cut out for you. Probably need to do something like Kubernetes or ECS or something and run your services there to have more control depending on your requirement. And serverless is very popular with event-based architectures. Yeah, you have a bunch of events, you push something and then an event is created, and for that event you want to run a process or whatever. That's quite good, and it's cheap as well. So I think that's pretty much it. That sort of concludes my presentation. Thank you very much for listening, and any questions? Any questions?
Actually, as the microwave is depending on the network,
Yeah.
and what is the take to control.
Yeah, definitely it will take, right? So rather than it being a monolith, one component talking to another is quite fast because it's the same process and it, in memory it get to that top. But microservices, that's not the case. There's a network latency that comes into play. And that's a trade-off that you have to make. That's it.
Any questions? So, I would like to give a token of appreciation to Stenilesh. So, I will invite Professor Chandana sir to give the token of appreciation. So, I would like to invite Professor Chandana sir to give a vote of thanks.
Good evening, everybody. So first of all, I would like to thank the audience. We can't have a talk if you are not here. And some of you are working, some of you are studying. Time is very valuable to you. And with all that burden, coming here and physically being present here is a great contribution to what we are trying to do here. Because we are the IT and Engineering Sectional Committee, we conduct most of our talks using Zoom online. But one big thing missing is the ability to network. We are on the network without networking. So to do the real networking, we have to get together. So that's one idea where we are going to have some of our tech talks in a physical mode. And of course, I want to thank Nilesh for a really valuable tech talk today for the seminar. I'll just give you an example why it is so important. So some of us here are working and some are students, but to have a good knowledge about the emerging technology is very important. Yesterday I was at a workshop connected to a very large project that is going to happen. It's a government project connected to climate change. So part of that is setting up a IT based data gathering system. So there was a presentation done and the audience consisted of ministry secretaries, additional secretaries, director generals, representative from the National Planning Department, External Resource Department of the Finance Ministry, really decision makers who spend, they don't spend anything less than 100 million. So because that is their approval rate. When something is above 100, they come to a meeting. So it is that kind of a meeting. And so I was seated in the back and there was a presentation. It was a very nice presentation where a person came and said how they would use things like Raspberry Pi based systems out there in the field to collect data, set up wireless networks to interconnect them, and use a lot of jargon like IoT, blockchain, things like that. And I can see the audience very impressed with them. But one thing they didn't realize is when the presentation was being made explaining Raspberry Pi was written with PIE, the one you eat, not 22 upon 7. So, and the project collect a lot of data, but that data is not flowing through a system. You need blockchain if data is flowing through, in fact, multiple systems, so that you can ensure its integrity, that it is being owned and transferred through authorized entities, things like that. Just you have a chain of devices collecting data does not mean you have to put it onto a blockchain. Those are two completely different things. So I think these kind of talks are very important to such high level government officials, because they make a lot of critical decisions on who gets the contract, what kind of system gets implemented, and without having this kind of knowledge, they might make decisions that we all regret later. So that's a very important thing, because the topic he talked about, the cloud native applications and all the other things connected to that, serverless computing, virtualization, all of that are the type of terminology that we hear when systems are being developed for the large scale clients like the government. So November 30th, we had to submit our tax returns. And there is a system called RAMIS, RAMIS, Revenue Administration Management Information System, operated by IRD, Internal Revenue Department. And it didn't work. It didn't work. It didn't work in such a spectacular manner that they extended the deadline, saying you can submit on 1st, but we'll take it as 30th. You can submit on 2nd, we'll take it as 30th. Now, they don't say anything, but I think still you can submit and it will be the 30th. So that is the kind of situation we have. So things like cloud native computing that Nilesh talked to us about and educated us are the technology that would salvage us. So if he was giving a talk to those top rank officials 8 years back, we would not have had that situation on the 30th. So thank you, Nilesh. It was really a good presentation for us. And finally, I would like to thank the IESL for facilitating this kind of interaction, this kind of talks, where we could come together and learn and make this country a better place. Thank you very much. And I wish you a safe journey back home.